Well, hi there. You have just watched 4 short videos concerning classification of numbers, and I thought we'd spend a couple minutes here going over some true-false questions which deal with this material. Uh, I would not be too concerned if you don't do well on this, because in our next class I'm going to discuss all this material, but let's give it a shot and let's see where you are with it, okay? So let me bring up the form I want you to be able to see, all right? And it's course group work 11TF. And you received that PDF from me. So here we are, and hopefully we're ready to go here on this particular sheet. And we will take a look at, okay, the material involving these different kinds of numbers. So as it says, having viewed 4 short videos from today's class, try answering these questions. The directions are: indicate whether each is true or false. You write T for true and F for false in the blank provided. So here we go. Let's give her a shot. All right. All the complete sets of numbers stated that follow are infinite sets that go on forever. The whole numbers, the rational numbers, the irrational numbers, and the real numbers. Yes, they do, right? Of course they do. So let's get on here. Let me see here if I can get my pen tablet working. Let's get a T in there for true. Okay. If you remove 0 from the set of whole numbers, you are left with the set of natural numbers, or the numbers that you learn to count with. So remember, the counting numbers begin with 1, 2, 3, 4, and so forth, dot, 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 go on forever. When you put 0 with it, that set of numbers, you do have the whole numbers. So this is a correct statement. It is true. The number -8 is a whole number. Well, that statement is false because of the fact that it is negative. Whole numbers start at 0, 1, 2, 3, 4, 5, 6, go on to ever to infinity, but they have no negatives in them, okay? The number, this is number 4 now, the number -8 is a natural or counting number. No, you never learned to count with negative numbers. So this is also a false statement. Okay. The number -8 is a rational number. Can you write it in a form, okay, that it is a fraction of the division of 2 integers? Isn't -8/1 a fraction that has 2 integers in it? It is, yes. So -8, it's true, it is a rational number. Look at number 6. The number -8 is an irrational number. Well, first of all, you must remember that irrational numbers written out in their simplest form are always decimals. And they are decimal numbers that go on forever, okay? They don't show any repetition, and they go on forever, jumping all over the place. So, is -8 an irrational number? No, it is not. So that is a false statement. Okay, let's go on. Let me bring this down to the next series of questions. The set of natural numbers is part of, or its members are contained in, the, oh, I can't see it because of my image being up there. They are part of the whole numbers, it says. Are all the natural numbers you can think of that you learn to count with, are they also whole numbers? Yes, they are. So this is definitely true. The set of whole numbers is part of, or its members are contained in, the set of natural numbers. Well, They all are except for what? 0. 0 is not a natural number. So, or excuse me, 0 is, yes, 0 is not a natural number. It's a whole number, but it's not a natural number. So this statement has to be false. The set of rational numbers is part of, or its members are all contained in, the set of real numbers. Well, for all the number types we've discussed so far in those short videos, the largest set of numbers that we are dealing with is the real numbers. It's everybody else, okay? So that is a true statement. The set of real numbers is part of, or its members are all contained in, the set of rational numbers. Well, any irrational number that's in the set of real numbers, all right, cannot be contained in the set of rational numbers. So this statement is definitely false. The set of integers is part of, or its members are all contained in the set of whole numbers. Well, half of the integers, all right, are whole numbers, starting from 0 and going to infinity in a positive direction. But the negative ones are not whole numbers, okay? Therefore, this is a false statement. The set of whole numbers is part of, or its members are contained in, the set of integers. Well, every single integer, excuse me, every single whole number is also an integer, okay? So therefore, that statement is definitely true. All right, let me roll this down a little further. The set of integers is part of, or its members are all contained in, the set of real numbers. Well, that's definitely true, right? Because every single integer is a real number, okay? So it is a true statement because the real numbers basically cover everybody, all right? The set of whole numbers is part of, or its members are all contained in, the set of real numbers. Yeah, that's true. All right. So no problem there. Any member of the set of irrational numbers cannot be expressed as the quotient or division of two integers. Well, remember, any number that can be expressed as the quotient of two integers or the division of two integers, the answer you get, and as a decimal or as a whole number, it may come out a whole number, but as a decimal, that decimal is either going to repeat or it's going to terminate, right? Okay, now it says here, any members of the set of irrational numbers cannot be expressed as the quotient of two integers. That's right, it can't be, because the irrational numbers produce decimals which don't repeat and don't terminate. So this is a true statement. Look at the next one. Some members of the set of irrational numbers can be expressed as the quotient of two integers. No way. No way. None of the members of the irrational set can be expressed as the quotient of two integers. So that is definitely false. Look at 17. The number 0.35 is an integer. Wait a minute, that's a decimal. How can it be an integer? Integers are either positive or negative whole numbers. So this is definitely false. The number 0.35 is a rational number. Could you write 0.35 as a fraction of the division of two integers? How about 35 over 100? Those are both integers, right? Therefore, this is a true statement. It is a rational number. Okay, let's go on. The number 0.35 is a real number. Well, it's rational, and rational numbers are part of the real numbers, so that's true. 20. This number here, all repeating threes, is a real number. Well, if we look at 21, the number 0.3 repeating says it's a rational number, and we know that's true because it's a repeating decimal. Repeating decimals are rational numbers. So if they're rational numbers, like 21 says, 20 must also be true because all rational numbers are real numbers. Phi, number 22, phi, is it a rational number? It is not. Remember, it is expressed as 1 plus the square root of 5 all over 2. That's the exact value of phi, right? And of course, phi has a radical in it that does not come out, quote, even. Therefore, that radical makes it not rational. Okay, so is phi an irrational number? Yes, it is. That is true. This number which follows shows repeating numbers forever after the decimal point. Must be an irrational number. All right, 65, 65, 65, 65. All right, 625, 625. The three dots mean it keeps going exactly the same way. That's a repeating decimal, right? And repeating decimals are not irrational numbers. They are rational numbers. So this is false. Each of the numbers shown here in problem 25 is an example of a rational number. Guess what? None of these numbers are rational numbers. They're all three irrational numbers. So that is false. Each of the numbers shown here is an example of an irrational number. Well, that's the exact kind of opposite of what we looked at in 25. So we know that's true. Okay, 27. Okay, each number shown here is an example of a real number. Well, if you look at all those numbers, they are all representatives of the different types of numbers. There's an integer in there, there are counting numbers in there, or natural numbers in there. There are terminating decimals in there. There are repeating decimals in there. There are fractions in there. They're all, right, real numbers, every single one of them, okay? So that's true. Each number shown here is an example of a rational number. Well, do you see any numbers in this list which are irrational? If you look at each of those numbers, they are all rational numbers. There is no irrational number shown there. All right, therefore, this is true. The set of natural numbers and the set of integers are both all part of the set of irrational numbers. Natural numbers aren't irrational. Integers are not irrational. They're examples of rational numbers. So this statement is definitely false. The set of natural numbers and the set of integers are both part of the set of rational numbers. They can all be expressed as the quotient of two integers. So therefore, that is true. All infinite sets of numbers, integers, rational numbers, and real numbers are all the same size. That is, all infinite sets of numbers are the same size. Now, we are not going to dwell on this topic. However, You saw in the last video you watched, a gentleman by the name of Georg Cantor came up with the concept of the fact that, okay, real numbers, okay, or excuse me, irrational numbers, okay, are huge sets of numbers, okay? So all infinite sets of numbers, the integers, the rationals, and the reals, are not all the same size because the real numbers contain the irrationals, and the irrationals and the reals are not countable, as it was said in the video. So they are not all the same size. The irrationals and the real numbers have a larger infinite size than the infinite sets of integers and rational numbers. We're not probably going to dwell on that, but it's something that you should have heard of because you're taking this course. And if we get some time towards the end of the course, I may come back and visit this more carefully. There are an infinite number of rational numbers located between any two integers located on a number line. When the last video you watched, the cartoon professor definitely said that that's a fact, that that's true. There are an infinite number of irrational numbers located between any two rational numbers located on the number line. And the cartoon professor indicated that that was a true statement. There are an infinite number of real numbers located on a number line. There most certainly are, right? You never could count them. They go on forever. But it is a greater size of infinity than the set of integers, than the set of rationals, than the set of counting numbers, okay? And like I said, we may return to that particular topic at the end of the course. So this is a true statement. There are more irrational numbers than rational numbers on a real number line. Well, both the irrational numbers and the rational numbers are infinite in size, but the irrationals have a greater size of infinity. And if we come back and talk about this, infinite set sizes are referred to as their cardinality, and the irrationals and the reals have the greatest cardinality. The irrationals are larger infinite sets than the rationals, which makes the real numbers larger than those two sets put together. So this is definitely a true statement. Well, thank you for going over those with me. I thought it would be interesting for you to take a quick look at what you just saw and think about some of these statements. Okay? Now, check back with the email you received today so you know what your assignment is. Okay? All right? So you take care, and I'll talk with you later.